Good morning everyone and welcome to the next session of Digital VE Days. It's day 3 today. My name is Silas Zorn and I will moderate this webinar today. Our topic today is designing of the MDI for power over single pair. Our speaker today is Simon Mark. Simon, good morning.
Good morning.
Who is working as a simulations manager at Würth Elektronik ISOs. Before we start with the webinar, a short info for you. You will be mute during the webinar. This means you cannot ask us questions via your microphone, but you have the chance to ask your questions anytime via the Q&A tool. This you can find this below on the right side on the question mark button. Today's webinar will be about 30 minutes long, and after that we will start with the Q&A session, with the short Q&A session. Last information for you, you will all receive the link to the presentation and to the recording of this webinar today. We will send us via email to you in the next days. So now I wish an exciting and interesting webinar. And now I give it to you, Simon.
Yeah, thank you. Yeah, welcome also from my side. I will show you in this webinar today about the design challenge or what you have to consider by designing the MDI circuit for SPE. And I will show you some new stuff, old stuff, because Ethernet is older than I am, and in this case I will show you a mix of both. We will go through 5 chapters, starting from Ethernet to SPE, then from looking onto the technical data, then comparison between automotive and industrial, then looking in detail in SPE, and then showing from PoE to SPE what happens there. Starting with some terms like SPE, well known is single pair Ethernet, PoE, power over Ethernet, POODLE is power over data line, SPoE, the same, this is the same background behind, but different meaning, is single pair power over Ethernet, but it's the same like power over data line. Starting from multi-pair Ethernet, going to automotive Ethernet, it was in the years 2010, 11, 12, in this time, 2-pair Ethernet was considered to use in automotives, so in cars, and they looked for the existing cable, like here the HG45 Cat6 or Cat5 cable, and they thought about, okay, it's too expensive for pairs, shielding around, not so good connector, and we have to reduce the size, the cost, all of them. And so they invited a new standard. It was the 100 base T1 and 1000 base T1. The cost reduction was there, and also the size reduction and cabling reduction. It was only 1 pair of cable, and you can see it is smaller, cheaper, and this was the beginning of single pair Ethernet in the car industry. Then you can see on the Ethernet or single pair Ethernet history, it started 2015, like I explained it, with 100 base T1 here in the corner. Then it was not enough for the speed data because of the cameras and all of the technology inside of the car, so they upgraded it or make a new standard for 1000 base T1. And then after, the industrial people said, okay, we need also some single pair Ethernet because it is very good in the car industry. It is cheap, easy. Why we cannot do this also in the industrial area? But changing it from 15 or 40 meter up to 1 kilometer to make it even longer, like the industrial area is long or not small. And so they started with the standardization, and 2019 was the standard for 10 base T1L and also for 10 base T1S. Later on, 2020, for multi-gigabit, 2.5 up to 10 gigabit. And 23 is the release of higher than 10 gigabits, but also for automotive, for 15-meter length, and 2024, so next year, the idea is to end the standardization of 10 base T1M. So this is for a multi-drop, up to maybe 20 participants on cable, and up to 50 meters. And also 100 base T1, but for longer range, not for, like here in the automotive, up to 15 meters, but even up to 500 meters to have this long range possibility of single pair Ethernet in the industrial area. For every standard, I think it's not working, my pointer. I cannot, now it's working, yeah. So you can see the wiring length of the cables or of the different standards. We have starting from 10 base T1L and wiring length of 1 kilometer or up to 1 kilometer. Some IC manufacturers said it can be up to 1.7 kilometers, but their standard is up to 1 kilometer defined. And if we go higher in data rate, we are also increasing the length. So if we are ending at 10 gigabits, we are only at 50 meters, but this is even high enough for car industry area or car area. Yeah. For the bandwidth, so for the frequency range, we need in different standards. At the beginning, for 10 base T1L, we have 20 megahertz. But if we go higher in the data rate, we are at 60 or even 600 megahertz, what is a big challenge for designing such cable, MDI, or the whole design of single pair Ethernet sensors or this environment. So this is more and more challenging. And if we are ending at 10 gigabits, we are here at 10 or higher than 10 gigabits, sorry, we are higher than 10 gigahertz. So this is a very ultra high speed, to say it, design challenge, and it is very interesting to look what happens in the future. Yeah, we will today look only on 10 base T1L and also short look on 10 base T1S and 100 base T1, but our main goal is to look on 10 base T1L to look what can be done in designing here the MDI circuit, all of what is necessary. You can see here the circuit for automotive, 100 base T1. We have on the left side the PHY, so the circuit, the IC. Then we have the MDI in the middle part and the automotive connector where you plug in the cable. In industrial pair Ethernet, or industrial multi-pair Ethernet to say it, in 400 base or 400 megabits, we have also on the left side our IC. In the middle part is our MDI, so the magnetics, and on the right side the connector. Here we see we have two channels, and in automotive only one channel. And so our idea was to use one channel like it is in 100 base TX and make it for industrial single pair Ethernet capable. To look on automotive SPE, there are some requirements you have to look for, that you are have done this, like the isolation, the decount mode attenuation, return loss, mode conversion, cheap and small, of course. And it can be done through several components you are including into the MDI circuit. Like for the isolation, you see here on the in the MDI you have the capacitors with an isolation of 60 volts. Then the decount mode attenuation through the decount mode choke and the decount mode termination circuit to ground. The return loss mainly through the decount mode choke and the capacitors. Then the mode conversion both through the decount mode choke and also through the decount mode termination circuit. And of course cheap and small, you see there are not so many components. They are designed to be very cheap and easy so that it can be produced in mass production or in in cheap for cheaper or lower money. But in the industrial area, you don't need very cheap components. You need robust and long duration commands, to say it. And our circuit was similar to the automotive circuit. So we have here the COM mode choke, the capacitors for isolation, but also a transformer to establish the 1.5 kV isolation, and also some ESD circuit to have an ESD protection. And if you look on the requirements, we have here an isolation of 1500 volts. So here the transformer T1. So this area is isolated from the IC, also from the all computing area with 1500 AC isolation or 2250 DC isolation. Then we have also the DC isolation of 60 volts of DC current through C3 and C4. Then also the COM mode attenuation is through 3 components established, like the transformer, the COM mode choke, and also the C1 and C2, which gives a good path to ground for the COM mode noise. Also the return loss through the components T1, C3, C4 and L1, and the mode conversions through L1, and also the ESD protection. There is also, if you go to power over Ethernet or power over data line, mainly power over data line, we have there a patent for a circuit design. And this is patented if you have here the transformer, the COM mode choke, and here going down some coupled inductor. So to prevent a patent violation, you can use the C3 and put it in between the 2 center taps so that you use only 1 capacitor. This is also possible, or even to use 1 capacitor on the line, on the upper or on the lower line, but this is only possible for lower data rates like 10 base T1L or S, because if you are going higher in frequency, then you can have mismatches and reflections, and so it would be not recommended to use this design for higher data rates. Here is a look of a board for single pair Ethernet. You can see the power supply, here in this case is over USB, then also the microcontroller, the PHY, the RX-TX mixing, which is necessary between PHY and magnetics, then the magnetics, so magnetics and the connector. If you look at from the side, you see the physical layer, so the PHY, the magnetics, and also the connectivity. Actually, there are several PHY chips available from analog devices, from Texas Instruments, and also from onsemi and microchip for 10 base T1S. And yeah, this is actually the status. I don't know, maybe there is also some newer coming, but this is the main. There are the main companies which are developing single pair Ethernet for 10 base T1, L and S. And yeah, if you want to design a single pair Ethernet circuit using chips and also magnetics, you have to look before you design what you want to do with this circuit in future, or in near future. If you want to use it for pure data transmission or also for power transmission, you can use it for only data transmission, then you can make it very small. So a small size possible, but then the problem is if you want to upgrade it to also power over power over data line and using maybe 50 watts or 30 watts, then it is problematic, because then you need different components. If you want to use it for SPOE, then it's depending on the power class, you have to select the components. So the rule of thumb is increase the transformer inductance, so use a higher inductive transformer. Then you can also use smaller coupled chokes So this is some rule of thumb. But if you only want to use this for data transmission, then you can use very small transformer. You can reduce the size, and it is also possible. Looking on the limits, so on the frequency limits for return loss and for reflection mode conversion, like here the red line is for 10 base T1L for the long range, and the yellow one is for T1S. You see they are in similar areas, but it is not so easy to say, okay, we can use 10 base T1L circuits also for 10 base T1S. And therefore I have for you in the next two slides the T1L circuit. So here's the MDI circuit for 10 base T1L. You can use this component, like here, the transformer with 350 microhenry or with 600 microhenry for higher inductive, higher inductive transformer, or for T1S if you want to use this for this shorter range and with more components, or like a multi-drop. You can use the 350 microhenry transformer and also neglect the common mode choke. It is also possible. And you can see on the limits, we are reaching all the limits, we are below the limits, and this is for T base T1S. Also for 100 base T1, we have a circuit you can use. Here you need a common mode choke, here named L1. And here we are also below the limits, and this is possible for 100 base T1. Yeah, starting from PoE to SPoE. This is the next chapter. For power over Ethernet, it is interesting how it works. It is like you see it here for 100 base TX. You have two channels, and the signal is going on the upper channel and also on the lower channel. I have shown it. It goes from right to left side, and also from left to right side. So they are going in both directions. But for power, it is different. It is going through one pair, through one channel, going down to the middle pin, and there going to the load, then back through the other middle pin on the other channel, and then to the connector. And it is easy to develop this for PoE. You don't need special components like here in SPoE. You need special components, of course, but different ones like in SPoE. And here, if you look on the circuit and how it is working, it is in some way complicated and a little bit tricky to establish a well-working SPoE circuit. So on the left side, we have also our phi, the connector on the right side, and in the lower region, the load. If we have here through the SPE connector, the data and power, it goes through the common mode choke, and then there is a low-pass filter in the lower area through a higher coupled or high inductive coupled inductor. Yeah. And the signal is going through the C3, T1, and to the phi, and not going down through the low-pass filter. During the powering, also the common mode choke, or the differential mode choke, sorry, is saturated. So L1 is saturated, so you have to be sure that your saturation current is not lower than your working current. So otherwise it will lose the inductance, and then you will have lots of problems, and also heating will occur, and so on and so on. The current is going here in this case through the lower cable. C3 and C4 are in DC block for the current, so the current is flowing through the L2 inductor to the load, then back through the L2 inductor and over the L1 common mode choke to the connector. So you see the current, the DC current, and also the signal are differentials through L1. You can see it here. There are differential signals through L1. But to prevent the signal go through the L2, you have to put the L2 in the circuit like in common mode choke, so that the differential signal is going through the L2 as a common mode signal, and also the current is going through the L2 as a common mode signal. Therefore, there is a common mode, there is a saturation, and so you have to be sure to choose a common mode choke with a differential mode choke with a good saturation behavior, like with iron powder or with an air gap, to have a very good inductive plateau up to this currents you are using for the PoE, SPoE. And also the next point is, if you want to find a coupled inductor for your design, you have to be also sure that it is well measured from the vendor, for the company. Here is an example, like this small inductor with 56 microhenry has a rated current of 1.36 amps. If you use it with this defined measuring circuit, or measuring PCB with 3 mm width and 35 micrometer height. If you increase the PCB, so the copper size, then you can increase also the current rating up to 1.6 amps. And if you even increase the copper to some copper chunks, then you have 1.9 amps. And in all three measurements, we have the same device, the same component. But you have to be sure, if you are choosing one inductor from different vendors, you have to look on the DC resistance and to compare it. If this is the same DC resistance, mostly it is not possible to have different current ratings, like here 1.36 from one vendor and from the different one 1.9, because the physical or the physics don't allow some cheating on rated current if this is the same copper size, the same copper wire, the same DC resistance. If you're then choosing an SPoE class for your circuit or for your whole application, you have here from class 10 to 15 two different voltage levels, like here 20 to 30 volts or 50 to 58, and also different power or current values. And for example, if you are choosing then class 14, you are powering it with 50 to 58 volts with a current of 0.6 amps, in summary 20 watts. And then you have to choose the right components with a rated current of 0.6 amps minimum, so that it is not heated too much during the whole powering, and you can work with it in a good environment, not too hot, so that the customer are not burned, or it is depending on the area where you're working. If you are in high temperature area, like in the desert, then you have to also look for the right current values for the components. And this is why you can ask us, call us, write an email we get then in touch with you and look for the right components, check what is your application. So this is not so easy for most designing processes. So we are offering you the service. You can ask us, you find the contact information, and we will help you. For example, if you're now choosing an inductor for 1.6 amps, you have two possibilities. You can use a small transformer with 350 microhenry, for example, and then common mode choke, which is a little bit bigger, to have this current rating. And then the problem is you need a very big inductor, coupled inductor with 220 microhenry, and it is heavy, it's expensive, you need lots of size, and you will not use this in your small application. So what you can do is you can increase the transformer size up to 2 millihenry, for example, and then the coupled inductor inductance is only 56 microhenry big. So you can increase it by by the inductance value, by size, by cost, by even by rated current values compared to the size or to the price, you will be for this solution much better. And yeah, this is what I also recommend if you are using high current circuits or an application for higher currents. You have to look for this application or this circuits, these components with higher transformer inductance and lower coupled inductance. I said class 14, if you want to look for 20 watts transmission, you choose, for example, a 600 microhenry transformer or a 2000 microhenry transformer. You can use the Calmode choke. In this case, it's both the same. And for the differential mode coupled inductor, we have here one with 220 microhenry with this article number, and for the same current value with 68 microhenry with a different article number, of course, and both are working in this design the same. But what you have here is you have here the higher inductance value, you have a bigger size of the transformer, but here you are mainly in the same size of components. But if you go higher, not from 0.6 amps but to 1.6, then it makes a big difference to choose the lower design with a higher inductive transformer than this above. But this is not the main problem for designing a circuit and also the MDI. It depends also on the components, of course, of the cable diameter and of the power class. And I choose here the class 14 by using in the beginning 58 volts for powering, so voltage in 58 volts, and our two components, the differential mode choke with 150 millihenry and the Calmode choke with also around 150 millihenry to make it easier. And on the other side, we have also our two components and voltage of 50 volts minimum for the powering component or powered component. And on both sides, we have 300 millihenry. So in summary, 600 millihenry. And all other voltage or losses are over the cable. And depending on the cable size, if you are using AWG 18 or 24, you have different losses per meter. And if you look on the table, we have for 18, so AWG 18, 230 meter of transmission length. If you go in for 22 or 24, we are decreasing in length up to or down to 57 meters. So you cannot say, okay, I power SPUE class 14 up to 2 kilometers or 1 kilometer. It is not physically not possible. Maybe if you are making this on the railroads, you're using such big cable diameters, maybe it's then possible, but you will not have the money to do this, or you don't want to use such amount of money to use this big of cables for 10 megabits. For class 14, this is also the comparison of the limits for the 600 microhenry and also to 2000 microhenry transformer. You see they are both in the limits for return loss and return mode reflection, and both are possible for class 14. If you go like explained to class 15, then we will only use the 2000 microhenry transformer, and it will be also possible to establish such a good picture. Here are for 10 base T1S and Poodle a circuit example which you can use to power up to, like here for L2, 0.6 amps. So this would be for class 14 possible. If you go higher, then you have to look for a different component. For 100 base T1. For L1 we have 1600 milliamps. For L2 only 0.45, so we are not in class 14, so we are in a lower class power range, so we can we have to choose different components to establish here also higher power classes. One of my last slide, only to give you an overview of the existing SPOE controller. We have two, one from analog device, a PSE controller, and also a PD controller for the power device, also from analog devices, and you can, or they are supporting all the classes from 10 to 15, so from 1.3 watts to up to 52 watts. So you have to use it for SPOE, but yeah, this is not only the only part. You have also to consider the MDI circuit. Also different EMC considerations are necessary. But in this case, we can help you. Ask us, call us. We will be there. And yeah, this was my presentation. I hope it helped you for the future consideration of single pair Ethernet design. And yeah, now is the time for questions.
Yeah, thank you, Simon, for the interesting presentation. Now we will come to your questions. Last information for you. If you cannot answer it all your questions, Simon will answer it then via email after the session in the next days. So now we can directly start with the first question. Who owns the patent with two capacitors?
Yeah, it starts from, or it was developed by Broadcom. In the time it was not 100 base T1, it was broader reach, and you find patents online. I cannot say where you can find it, but I have seen it, and they are patented by Broadcom for this powering circuit, and yeah, this is my information.
Okay, next question. Are the ICs that are compatible with 10 base T1L also compatible with 10 base T1S?
No, unfortunately not, because for 10 base T1L you are, it's possible to power up to 1 kilometer or higher, and you have different voltage levels, and also for the limits it's a little bit different. So if you look on the datasheet for the analog or Texas Instrument devices, what I found was only for 10 base T1L. But if I found different information, I will look on it and give then a response, but at the time I have no other information.
Okay, what is layout consider?
Yeah, this is not so easy to say it here. Yeah, you have to define this layout because you have to consider all of the circuits around this. So for the PHY chip, you have to look. You are using a 4-layer PCB or a 6-layer PCB. Is this an SPI? Is this an integrated MAC-PHY, or is this via MII or a different transmission protocol? And therefore you have to look also on your design. We are working on a design example or a layout recommendation for you, but we will inform you in the next month about this. So we are working on it, but I cannot say a 100% answer for this.
Okay, next question. Does the circuit for SPOA apply to PSA and PD?
Yeah, depending, of course, for the PSE, you can look for a bigger component. Like for the PD, mostly the PSE part is inside of a switch where you have different different channels or different outgoing cables, but for the PD you have only one cable, and so mostly the PSE component for the inductor is, for the coupled inductor, is bigger, and you can use bigger coupled inductors, but in our case we are looking that you can use the same component for PSE and also for PD side.
Okay, next question. Layout design consideration.
Yeah, this is also what I will give then later, maybe in several months, an update about the layout considerations, and also, yeah, you have to look for the distance of to establish this 1.5 kV, then the EMC consideration, differential pair design, and or yeah, differential layouting, and so on. But this is not in this in our webinar the point, but it will be in future in different webinar where we will give you an information.
Okay, then I would say we are finished with this webinar when you have no more questions. Thank you, Simon, for your time, for the interesting presentation. Thank you for your attention. I hope you enjoyed it. And yeah, hopefully we see you in the next session. Thank you and have a nice day.
Yeah,
bye
thank
bye.
you. Bye.